Logistic regression. So what is logistic regression? It's an algorithm that learns a linear model that can be used for classification and probability estimation. So let me just give a little example of that. If your data contains two variables, x1 and x2, and they range from 0 to 1, that would define this space. See, x1 goes from 0 to 1, x2 goes from 0 to 1, and so all your samples will be in this space. And often that's called the instance space. In this case, it's a two-dimensional instance space, but it could easily scale to 3, 4, 5 n dimensions, whatever you want. A linear model cuts the instance space with a single, line or plane or hyperplane, depending on what your dimensionality is. So in this case, that line there is a linear model, and you would say everything on one side of it would be classified as 1, everything on the other side of it would be classified as 0 if you're doing classification, or if you're doing probability estimation, right on the line you'd say you're 50-50 between 1 and 0, and as you get further and further in this direction away from the plane or hyperplane, you'd have a higher probability of predicting 1, and similarly for 0, as you go in this direction, you'd have a higher and higher probability of predicting 0. So that's what logistic regression is trying to learn. That's the way to think about it. And what is logistic regression good for? Well, it's very effective in practice. I'd say there's 3 major types of models that I see used all over the place. And of course, there's champions for other model types, but in my experience, I'd say logistic regression, some kind of boosted trees, and neural networks are kind of the trinity of things that are being successfully applied all over the place across multiple domains. And I know, so I'm going to get one of you SVMs, blah, blah, probabilistic, blah. Yeah, there's many things. There are many things, and let all flowers bloom. But if you want to triage your time, and in fact, I have triaged your time for you by deciding what to teach in this course, I'm going to show you those 3 important model types and machine learning algorithms to start your toolkit off with a pretty generically useful set of things. So when would you use logistic regression? All of that aside. I mean, if the problem really is linearly separable, but you won't really know that because your instance space is going to be much larger and crazy, and nothing really is linearly separably. But if there are a lot of relevant features, tens to hundreds of thousands, you'll often find that logistic regression does a pretty good job. And one of the interesting things about high dimensional spaces is that they're highly counterintuitive. So something that is extremely nonlinear in 100,000 dimensional space, you can approximate it quite well with a linear separator that you've learned through logistic regression. Another good thing about logistic regression we'll see is compared to some of the others, it's a very efficient thing with runtime. That is, when you're applying the model in practice, it can go very, very quickly. And it's also relatively easy to learn compared to boosted trees and neural networks and some of the other options. And another good thing about logistic regression is you can always use it as a simple, effective baseline. When you get into doing machine learning, one of the bad habits that you might want to break is you want to immediately jump to the fanciest algorithm and apply the most complicated thing to your problem because that's what really smart people do. And so I'm going to go and be like, oh, I did neural networks, blah, 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 BERT, whatever, blah, convolutions, blah. Not necessarily the right thing to do. Often you want to try the simplest thing you can possibly make work and see how you're doing. And then let the problem, let the data, let the errors guide you to add more and more modeling complexity. So logistic regression is often a great place to start. That said, logistic regression will generally not be the most accurate thing you can do. But sometimes you don't need hyper accuracy. Sometimes you just need something that adapts to a time-changing problem. Or sometimes, just the shape of your problem makes logistic regression, and the constraints of the application you're working in makes logistic regression really the right tool for the job. And I'll say, I currently today manage teams that have many logistic regression model deployed. And I'll say my very first job 15 years ago when I was working on fighting spam, we used logistic regression. So it's stood the test of time, and I bet it'll be around in 15 years and people will be doing it. So what is logistic regression? Remember I said in the last lecture that in machine learning algorithms have three things to talk about. So this slide, I'm going to tell you everything you need to know about logistic regression, and then you're going to be able to go and implement it. I don't need to do anything else. 2-slide lecture done, because logistic regression is a linear model with sigmoid activation. The loss function you need to use is log loss, and the optimization method to use is gradient descent. Done. Poof, go. Just kidding. I'm going to go through all of these in a lot more detail, but it is a nice way to think about a learning algorithm where you can break it down like this. And to somebody who's been doing machine learning for a long time, saying these things are like, yeah, I get it. I know what to do. So often you'll see like, hey, I'm doing logistic regression, but I've changed the loss function. And those are the types of conversations you can have with people who are trying to innovate on the basic machine learning algorithms and customize them for their particular use cases. But let's go through the simple version first. How about that? And we can talk about fancy stuff later, maybe in your next machine learning course. So like I said, logistic regression is a linear model. And this is the math that represents that line or plane or hyperplane or whatever it is that's going to separate, instances of one class from instances of another class. An instance, sample, training data, feature vector, these are all sort of synonyms. So, you take your feature vector, it has x1, 2, 3, 4, 5. That defines a point in the instance space. Sometimes that point would be called, there's my instance that I'm trying to classify. We'll just, like I keep saying, we'll just keep giving the terminology. I try to speak like how I would speak when I'm talking to professionals so that you can hear it and you can let it soak in. But I will keep slowing down and saying this. I hope it doesn't get too repetitive, but I know there are a lot of terms. So every time I catch myself, I'll slow down and re-explain what it is. So, if you remember from when you were a kid, you'd have, well, at least with y equals ax plus b. And that was the form of a line in a plane. So that function is a great way to specify a line. And b is equivalent to weight 0 here, and ax is equivalent to that part over there. So really, this is just a slightly fancy version of a formula for defining a line or a plane or, a linear separator. And that's where this comes from. So let's see. You have one weight per feature. And so if you have, if you're doing a spam, SMS spam, and you have thousands of words for for your features, each of those words will have its own independent weight. And that weight will say, how much should I consider this feature when I'm trying to make a determination of, is this message spam or not? These weights are often also called the parameters of the model. And if you remember from the last lecture, we talked about the parameters of the model and then the hyperparameters of the modeling process. And I write these things and nobody can read that handwriting, but I try. I try. Here, I'll erase it. So the hyperparameters of controlling the modeling process, and we'll get to in a few slides what are the hyperparameters for logistic regression. But the parameters of a logistic regression model are the WIs as well as the W0. So if you have a training set that has 10 features, you would have 11 parameters in your model, one for the weight 0 and one for the other weights that are associated with each feature. Weight 0 is often called the bias weight. And if you think of, y equals ax plus b, the b would sort of control how far you shift the plane from the origin, and then the weight determines kind of the angle of that plane once you've kind of shifted it based on the bias. And so that's why it's called the bias. Without the bias, all your linear things would go through there, which you don't really want. Okay, so that is that. And I said on the previous slide, this is a linear model with sigmoid activation. And so what does that mean? It means that when you have a new instance, you calculate this value and then you pass it through a sigmoid function. And that the output of that sigmoid function is the y hat. And remember, the y is the label, and the y hat is your model's estimate. the label, or your prediction. The hat means it's the prediction, and the y is the true label, or f of x. Okay, just a little more really amazing handwriting. Moving on. So what the heck is a sigmoid function? A sigmoid function takes a value that has an infinite range and compresses it down into a 0-1 range. And the way it does it is that if the input here is 0, the output is, in this case, it's 0.5, but you could have different versions of the sigmoid function that change some of this equation a little bit to shift this around. But in this case, since we're trying to do probability estimation or binary classification, we want to keep this so that it's 0 to 1, and at the middle point it's at this 50%. So if the output of applying the linear model is 0, then you would pass it through the sigmoid and you'd get this point, which is 0.5, and you'd say, hey, I don't know, it's right on the dividing line, so it could go either way. Whereas if you have a larger and larger output from your linear model, you would eventually start to asymptote, and this is 1.0. And similarly, a very large negative would asymptote at 0. So that's it. I mean, that's the complete representation of the logistic regressions model. Linear model, plane, distance from the plane essentially, pass through a sigmoid that turns into the prediction of the probability, and then you can turn that into the classification using a threshold, and we'll see that in a second. So here's an example. If we have this as the linear model, we would say, and here's some instances, or here's some test data, and we want to say, well, what would this model say on this test data? So weight 0 is 0.25. So if we're talking about this first one, we'd say 0.25, because that's the W0, so it all has that, plus then weight 1 is -1 and x1 is 1. So we'd say we multiply those, so we add -1, then we do plus, that's 1 times 1, so plus 1. So that would be, these would cancel out, and the answer here is 0.25 is the output of the linear model. Now we need to pass that through the sigmoid, so a 0.25, I don't know, maybe it's around there, go up to there, something along those lines. And so the output would be something like, I don't know what that is, 0.64. So why don't you work through a few more examples on your own time? And I won't necessarily do them all, but pause the video, work through these examples, start to get a sense of what the outputs are. Okay, so now you've got this all figured out. The next step that I mentioned briefly is the threshold to turn that 0 to 1, which you would interpret as a probability estimation, and you want to get a classification out of it, you can use a threshold. And I think in general, for most everything we do, we're going to just use a threshold of 0.5. Although when we're making some ROC curves later on, we may vary the threshold so that you can see different trade-offs that are possible. But essentially, if the output of the linear model is greater than 0, it's above, the output of the sigmoid would be above 0.5, and you'd predict 1. If you wanted to change the threshold, you could change the threshold to be like 0.9. Then you'd need to have the linear model output at least a 2 in order for the complete logistic regression model to predict 1. And if the linear model output any value less than 2, then the logistic regression would predict 0. So let's go through a few more examples of linear models, and this isn't really required. This isn't important necessarily to be good at machine learning, but it just helps you think a little bit about what's going on and what can this represent and how do these weights interact. So we're going to go through a series of examples, and I want you to look at this as the model. So weight 0, the bias weight is 0, weight 1 is 1, weight 2 is 0, and then the threshold on all of these is going to be 0.5. So with this as the instance space, which part of this instance space would that model classify as 1 versus 0? Or, in this case, green versus red. So think about this. If you, the bias is 0, so we're kind of like, starting at 0, and then as x2 increases, we're multiplying it by 0. So as x2 increases, it doesn't change the output of the linear model at all. So along this line, the output of the linear model would be 0. And, it's right on the threshold, so you wouldn't exactly know which way to predict. But any step in this direction, times you're multiplying feature 1 by 1. So any motion along that axis, any value of x1 greater than 0 is going to push the output of the model greater than 0, going through the sigmoid with the 0.5 threshold. You're going to classify every point over here as green in this case. So if you're dealing with an instance space where there's 2 features and the feature values range from 0 to 1, and you have this model over here, which I've kind of made a little hard to read, then it's going to just classify everything as 1 as green. Probably not that useful. Okay, let's deal with this model. And this model is the same as the last one, except that we have the bias weight of negative 0.25. So again, going in this direction doesn't do anything. Going in this direction, you start off at negative 0.25. So once you get to 0.25, this is the line where the answer is 0, where, if x1 is 0.25 or less, the answer would be negative, and 0.25 or more, the answer would be positive. So in this case, that would be the classification produced by that logistic regression model. Do another one. I mean, this is, we're just moving it over even further. So that's what's happening with that. Now let's get to a slightly more interesting case where we're incorporating both variables. In this case, we'll say the bias is negative 0.5. So that's, essentially this model there, but now we've turned weight 2 from being 0 to 1. And so that means there's 2 ways for the linear model to get up to the point where the sum is above 0. And that is if x1 is greater than 0.5 or if x2 is greater than 0.5. And then all the different kind of like trade-offs between those 2 things getting up to those values. And so this is where you start to get separating planes that are not axis aligned, is when you start incorporating more and more of the weights. Do this again with a larger bias weight, and you can see that whole thing will just shift up. Similar to, this one, it shifted it over. In this case, it shifts it diagonally. And then if you make weight 2 be negative 1, okay, now stop and think about what this is going to do. And I'm not going to walk you through it, but press pause, think for a second. When you think you have the answer, click. There you go. It just changes the direction of that separating plane. So fine. And just a few things that I've mentioned before. When we're dealing with 2 dimensions, the separating plane is a line. In 3 dimensions, you could imagine a cube with a plane cutting the cube, and changing the 3 different weights would move the plane, and changing the bias would shift the plane. In n dimensions, it's called a hypercube, but it's the same thing, just that a human brain doesn't know how to visualize it. So, it's harder to deal with. So you're like, what are you talking about, Jeff? I'm taking a graduate level course to learn machine learning, and you're showing me a line. How is this going to learn anything meaningful? What are you talking about? But the notion is that high dimensional spaces are really counterintuitive. And so one way to talk about it is the curse of dimensionality. And every time you add another dimension, and in this case, adding another feature. So if we're doing spam, the SMS spam thing, and you have 10 features, you have a 10-dimensional space. Now add an 11th feature, one more word. It's just one more. 10% increase in the number of dimensions, but the space that's represented, every time you add another dimension, it essentially doubles. So as you add more and more and more features, the instance space gets large much, much more quickly. And that has a couple properties. One is that it creates a lot of sparsity between the instances. That is, every time you add a dimension, things that seem close get further and further and further and further and further and further in this high dimensional space. And that gives you a lot of ways to put linear separators between points that you would say, like, look, in 2 dimensions, those are right on top of each other. Yeah, but go to 30 dimensions, and there's a whole bunch of ways to separate those 2 points with linear separators, which seem so simple, but they're able to weave between the sparsity of your data points and create very accurate separators. Another aspect of the curse of dimensionality, which isn't quite maybe as relevant, is that as you go to higher and higher dimensions, the distance between points becomes more and more similar because, I don't know, well, we don't need to go into that, but this counterintuitive property of high dimensions is why these very seemingly simple models become one of the most important machine learning techniques that people are using today. Neural networks are pretty darn important, but logistic regression is pretty darn important. Okay, there you go. There's the 3 things to talk about: the model structure, the loss function, and the optimization. And we've just finished the model structure. So we're 1/3 of the way through logistic regression. And, the model structure is pretty simple. You have 10 dimensions, then you'll have 11 parameters, 1 weight per dimension, and then that extra bias weight. That's all there is to it. So the rest of this system, the loss function and the optimization is going to be to figure out how are we going to set those 11 things to something that is predictive of the task that we're trying to accomplish. So now we're on to the loss function. And remember, the loss will look at the output of the model at any particular point and say, how good are you doing? Are you getting a high score? Are you acing this? Or are you doing a really crummy job and you need to go further? You need to make a lot more improvements before you have a model structure with the right parameters to represent the problem well. So remember, we talked about accuracy as a potential for this. Accuracy is nice because it's intuitive, but it has a lot of bad properties for optimization. So we're going to do something a little bit more fancy. It's called the log loss. Now let's go through this step by step. Just a little reminder that y hat is the prediction of the y. That's the output after running the linear model, passing it through the sigmoid, you get the y hat. And that y hat is what we're going to use in the loss calculation. Now remember, if you're doing classification and applying a threshold, you might have a different notion of y hat, which is the 0, 1 that you get, but you don't use that with the log loss. All of this happens before the thresholding, or you're just not gonna, it's wrong. Okay, so log loss is got 2 conditions to it. And one condition is if the true label is 1, then your log loss is the negative of the log of your prediction. So you take a training sample, a single sample, you pass it through the model, you get your prediction, you compare that to the correct label for that sample that you're trying to learn, or that you're evaluating on. If the correct answer is 1, then you do negative of log of your answer. And so here's a visualization of that. Here's the y hat, and remember that y equals 1. So if y hat equals 1, you're getting it right. You have the right answer, you're doing everything perfectly, and your loss is 0. So loss, it's kind of like you're adding up your score, but really the score is bad. So you want your score to be 0. You want your loss to be 0. So, if you predicted the right answer in this case, perfect, loss is 0, wonderful. If you predicted 0, you are as wrong as you can be. Like, you couldn't be any more wrong. And the loss is going to be a pretty darn high number. But you'd see that as you get more and more wrong, your loss increases sort of in an exponential-ish fashion. And that is that. The other case is if y is equal to 0. So if the true answer is 0, then you just essentially flip this. So you do 1 minus your answer, which is doing the top thing with just a flipperoo. And so if the true answer is 0 and you predict 0, you got 0 loss, you're doing perfectly. If you predict 1, you're going to get a lot of loss, that's no bueno. And if you're like predict 0.5, you're going to get a loss of like, I don't know what that is, like maybe 0.55, something along those lines. So that's how it goes. Let's do a couple examples. I'll walk through 1 or 2, and then you guys can do them at your leisure. When I do walk through examples like these are good things to really know how to do because they're the type of things that are easy to put on a test. You know what I mean? If I'm like sitting around saying, oh, I got to come up with 15 more questions, what should I do? Well, hey, this is pretty simple. Let's do it. Great question. So, take the time and make sure you understand this concept. So in this case, the first one here, if the true answer is 1, but we've predicted 0.9, what is the loss? So we're dealing with this first case because the true answer is 1. That's this upper thing here. We've predicted 0.9, and the loss is some value right there, something pretty small. And we'll fill it in. I happen to know it's 0.105 because I had a calculator when I was making this slide. This case, we got a little bit more wrong. We predicted 0.5, but the true answer was 1. And the loss is significantly higher. So take your time, press pause. I'll get out of the way so you can pause it without my big old head. And walk through these next two. And try to get the right answer. Boop. Okay, and click. And click. So you can see that in these cases, we were a lot more wrong and the loss went up quite a bit. Just a quick note, when you're implementing this, use the natural log base E, so that we all kind of have the same answers. All right, so here we go. This is just the summary of the second part of this model, which is the loss function. We're using log loss, and that's defined as if y equals 1, the negative log of y. If y equals 0, 1 minus that, the negative log of 1 minus that. And here's a little fancy math trick. You can basically, by doing this, you accomplish this if statement in a single line. And in general, when we're talking about what's the loss, you would want to talk about, I think, the average across your data set. So if you were running this on your testing set, you would iterate over every sample in your test set. You would get the prediction of your model on that sample. So that's, y sub j hat. You would look at the true label of that sample, sum them up, and then divide by the number of samples in your training set. And that would be or the test set or whatever you're working with. And that would be the average loss that your model has on those samples. And that's a good thing to do because if you don't do this averaging, then the loss would change as you change the number of samples in the set, and it's a little bit harder to sort of interpret just because, oh, you got more data, your losses went way up. So, it's just a helpful thing at this point. And then, we're going to see in the future where we'll get there. All right, so there you go. 2 steps down. Model structure, linear model, loss function, log loss. Pretty simple formula. You have a little intuition about how it works now. And now the optimization method. And for this algorithm, we're going to use gradient descent. Here we go. If we have a training set that just has one dimension, so every sample in your data just has one feature, and it's called x1, and it ranges from 0 to 1, for example. And we have this model as the starting point. So weight 0, the bias weight is 0.25, weight 1 is -1. Now you could draw on there, if you thought for a minute, what that model will do, which ones it'll classify what way. And I've already done that. So it'll create this line at 0.25 because of this weight, and everything that gets more and more below it predicts 1 because this has the -1, so it flips from what normally happens, and everything above here is predicted 0. Okay, fine, beautiful. But we're not talking about that anymore. We're talking about gradient descent. So what happens if you vary weight 0? Let's try a bunch of different weight zeros because we're trying to find the weight 0 that optimizes the loss on this data set. Now, if I calculate the loss and I vary weight 0, and each x here is a point, so I've tried all of these different possible values of weight 0. I tried 0.2, here's the current value, tried 0.3, tried 3.5, etc., etc., etc. And this is a kind of brute force way to optimize this, but it could work. You try out, 10, 20, 50 values for weight 0, and you essentially would say, well, that value of weight 0, which happens to be 0.1, gives me the lowest loss on the training set. So maybe 0.1 is a better value than 0.25. That's kind of the starts of gradient descent. So we could do the same thing varying W1. We could do them both simultaneously. So we explore changes to each of the weights independently. And in the case of W1, we see that, that's the best point that we found so far. And it's probably the case that the best point is actually in one of those gaps, either there or there, but we didn't try them. So, we'll come up with a better optimization way for this. Then you'd say, okay, well, let's go ahead and update the model. We found a different value for each of the 2 parameters in the model. So there you have it. We found better values for W0 and W1, all the parameters of the model. Let's update the model. And this version of the model should have less loss on the training set than this version of the model. And so we've made an improvement. We've done a gradient descent, the gradient in terms of the loss function. We're heading towards the minimal value of the loss function given all the options that you have among all the parameter settings that you could possibly use. And what this would do is, of course, move this thing over that direction and, scale the points even further. So, the probability goes up faster as you get away. And that apparently is better. It's not the clearest training set, but believe me, less loss doing that. Okay, but we're clearly not going to do that. We're not going to do a brute force discrete optimization because we have math. There's people who love math, smart people who've come up with a much better way to do this. And the way to do that is to take the derivative of the loss function with respect to the model weights. And so what that means is that allows us to find the direction where we change the parameters of the model to most reduce the loss. So once we have that derivative, we'll know the gradient is in that direction. We won't know exactly how far away it is. So we'll take a step in the direction, but taking the derivative of the loss with respect to the model parameters helps us figure out, well, that's the direction of the gradient. Let's take a step. Okay, so derivative of the loss function, the loss over the training set with respect to the parameters, and sometimes that capital theta is used to represent all the parameters that your model has. In this case, it's weight 0 plus all the other weights, all the W's. So we want to know which direction is the gradient, which direction of change of the model parameters most changes the loss. And it turns out you can calculate the partial derivative in terms of each weight separately. So that's a nice property of what we're doing here. There's not interrelationships. So then you go on and you do a bunch of calculus you don't need to remember. It's not really a bunch of calculus, but we don't need to dredge up those old terrible memories in all of our brains. Okay, and then you come up and after you've done a few steps of calculus, you end up at this. And what this says is the gradient for weight I for training sample X is you figure out your prediction for training sample X, you compare it to the true label. If you're close to right, that means that you need to make a smaller change for this particular training sample. So if you're absolutely right on this training sample, then you'd say, we're not going to improve the loss by messing with anything according to this training sample, so don't touch anything. It's perfect according to this training sample. But then on the other hand, if the delta between them is large, like 1, then you would say, well, geez, on this training sample, I've made a mistake, and it's a very large mistake. And so in order to reduce the loss, I need to have a large change to the weights, or, related to this particular training sample. And so how do you do that relationship? You say, well, I need a large change of the weights, and I'm going to change it based on the particular training sample's value for variable xi that helps me most reduce the loss. So it takes a step it sets the gradient to be in the right direction, that, the bigger my mistake, the more I want to go in that direction, and the direction is based on the feature values of the instances that we've gotten wrong. So that's what this essentially figures out. And then what you would do is you would take the average across the entire training set. So For weight I, you want to figure out what's the direction of the gradient for weight I that has the largest effect on the loss according to the training set. And you would go through each instance in the training set, each training sample that you have. You would calculate the gradient with respect to the weight that we're talking about. So it's weight I. So we would look at training sample J according to the jth training sample, and we would look at its ith weight, and we would figure out, well, how wrong or correct are we on this training sample? What is the value of this particular instance for that feature where I was either right or wrong, and then accumulate that towards the gradient. Then, of course, divide by the number of samples, because you don't want your gradient to scale as the number of training sample scales, or I mean, you can do it. You don't necessarily need to do this, but could be a mess. Harder to figure out what hyperparameters to use. So right, for now, take the average across the training set. So in this sense, you found the change that you want to make to WI to most reduce loss on the training set. Great. So of course you need to do it for each weight, but you can do this in one pass over the data by calculating the gradient for all the weights simultaneously. And then once you've calculated the direction that you want to take a step, which is the gradient, but let me tell you one thing. When I first implemented this, you got to think for a second. The gradient is what direction? Is it the direction that most increases the loss or most decreases the loss? And the first time I implemented this, I promise I did gradient ascent. And I was like, what? No, but make sure you take a step away from the direction that is increasing the loss. And so that would be negative alpha, which is a parameter, which is the size of the step you want to take, times the gradient that you found. And so weight I after one step of gradient descent equals weight I before the step of gradient descent minus the step size times the direction of the gradient. So unfortunately, I'm right here in front of the screen and you cannot read this, but let me read it to you. It says, note, x0 equals 1.0 for all samples. And what that means is that for the bias weight, weight 0, when you're doing this calculation, you use 1.0 for every sample in the training set. And that's just the way that you need to calculate the gradient, because that bias weight is added into every linear model calculation, essentially as if there was a 1.0 there, an extra 1.0 on the sample. So that's how you think about dealing with that weight. That's a common question, which is why I'm belaboring it slightly. I mean, that plus gradient ascent are two kind of common problems you might bump into. Okay, and there you go. Logistic regression. And so the way that you would run logistic regression is you would create a linear model with the right number of weights. You initialize all the weights to 0, including weight 0 through weight whatever it is. Then you just run a little loop until convergence. And convergence means that after each step of the loop, you check the loss on the training set before and you check the loss on the training set after. And if the decrease in loss is too small, then you've converged and you stop running the algorithm. And then each step of the loop, you find the gradient for each weight by averaging across a training set, just as I described on the last slide, exactly like I showed you there. And then you update each weight by taking a step of some size alpha in the other direction from the gradient, not gradient ascent, we're doing gradient descent. That's it. Now, in order to control this modeling process, you do have a few parameters, and these are called the hyperparameters. Hyperparameters of the logistic regression model learning algorithm, machine learning algorithm. One of them is this alpha, which in the framework code is called step size. And so that should be some value, probably like, 0.11, something like that. And that's found the gradient. How much do I want to change each weight in the direction of the gradient? Another parameter is the convergence, where we say until convergence. So that is, keep going until you're not improving the loss very much. That means you're probably getting near the optimum. And in fact, in the case of logistic regression, there is a single optimum. and you will converge to it using this algorithm, assuming you set all the parameters correctly and you're not like your step size isn't too large, so you're not getting down into the actual optimum and you're not just bouncing around it. And then the final thing that you might want to consider is the threshold for the value between 0 and 1 to do the classification. If we're doing classification, which, in the SMS spam case, we are doing classification. So you'll have to have a threshold somewhere in there. That's it. Logistic regression, your first actual machine learning algorithm. The homework assignments in module 1 will go through building logistic regression and then applying it. Thanks for sticking with us. Good luck.